Today we start a series of 3 videos on advanced thermodynamics. We've looked at thermochemistry before, and we're familiar with the concept of enthalpy and enthalpies of formation. But now we're going to look at 2 other factors. One is called entropy. We'll be introduced to that today. And the other one is called free energy, which we'll learn about later on. Mostly what this unit is about is studying the factors that determine whether or not a reaction will spontaneously occur, and then being able to use what we learn to make predictions about the spontaneity of a reaction. Because this is going to be the main focus here, let's define what we mean by the word spontaneity. In everyday life, we use the word spontaneous to describe, say, a person that, just kind of does random things without thinking about the consequences, or someone who's just up for any activity at any time. But in chemistry, spontaneity means, will the reaction proceed? In particular, spontaneous changes are ones that occur without continuous outside assistance. So you don't have to constantly help them along to keep them moving. Examples would be objects rolling down a hill. Once you start a ball rolling down a hill, it will keep rolling down a hill without you continuing to roll it. An object rolling up a hill would not be spontaneous. You'd have to keep working at that to get it to the top of the hill. Combustion reactions. Once you light a campfire, for example, it keeps burning once it gets going. You don't have to hold the match there for the entire campfire. Another process is a phase change would be ice melting at room temperature. That spontaneously happens at room temperature. Ice spontaneously forms, in other words, water freezes spontaneously at temperatures that are below 0 Celsius. So those are all examples of spontaneous processes. One of the big focuses of this unit is to investigate what determines if a reaction is going to be spontaneous or not. And there are 2 main factors that we can explore here. One of them is potential energy changes. Changes that result in less energy being stored in the system tend to be spontaneous reactions. And the reason for that is because lower energy systems are more stable. This is something that we learn early in our lives. Things fall down, things don't fall up, for example, to use gravitational potential energy as an example. So anytime all other factors are equal and we see potential energy lowered in a system, that will tend to be a spontaneous reaction. So exothermic changes tend to be spontaneous changes. However, that does not account for all the spontaneous changes that we know about. An example would be ice melting at room temperature. Ice melts spontaneously at room temperature. You take a piece of ice, put it in a room, set it on a table, and it's going to melt without you providing any outside assistance. So why is that process spontaneous even though it's endothermic? Because energy has to come in from the room to make the ice melt. Well, the other factor is something that we give the name entropy. And I'll define entropy a little bit later on, but first I want to do a little thought experiment for you. Think about a deck of cards. When you buy a deck of cards, there are 52 cards in there, and those cards are all stacked in order by suit and by value by the card manufacturer. Now let's take that deck of cards and just toss it up in the air and let all the cards fall down randomly on the floor, and then just sweep them up into a pile and reform that into a deck. And then let's ask the question, what are the odds that you would get an ordered deck of cards spontaneously happening just by sweeping all the cards together? Well, let's sneak up on this by thinking about what if there were only 3 cards? If there were only 3 cards, these are the possible ways they could be organized. You could have card 1, then 2, and then 3. That's one possibility. You could have 1, 3, 2. That would be another possibility. You could start with 2 and then have 1, 3, and 2, 3, 1. And you could start with 3 and then have 1, 2, or 2, 1. So it turns out that you would have a 1 in 6 chance of having an ordered deck. There are 6 possible ways to have it organized, and 1, 2, 3 is the ordered one. Well, let's expand it. What if there were 4 cards in the deck? Well, if we started with card number 1, we could have 1, 2, 3, 4, which is our possibility of an ordered deck. Or you could have 1, 2, 4, 3. You could have 1, 3, 2, 4, 1, 3, 4, 2, or you could have 1, 4, 2, 3, and 1, 4, 3, 2. If our deck started with card number 2, we could have 2, 1, 3, 4, or 2, 1, 4, 3. We could have 2, 3, 1, 4, and 2, 3, 4, 1. We could have 2, 4, 1, 3, and 2, 4, 3, 1. If we started with 3, we could have 3, 1, 2, 4, and 3, 1, 4, 2. We could have 3, 2, 1, 4, and 3, 2, 4, 1. We could have 3, 4, 1, 2, and 3, 4, 2, 1. And if our deck started with 4, we could have 4, 1, 2, 3, and 4, 1, 3, 2. We could have 4, 2, 1, 3, and 4, 2, 3, 1. And we could have 4, 3, 1, 2, and 4, 3, 2, 1. And there aren't any other possible ways that we could organize 4 cards than this. So we have 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6. We have 24 possible ways that this could be organized. Only one of them is the organized deck, so we have a 1 in 24 chance. When we had 3 cards, we had a 1 in 6 chance, and 3 factorial is 6. Now that we have 4 cards, we have a 1 in 24 chance, and 4 factorial turns out to be 24. So we could say that if we had n cards, we would have an n factorial chance. We would have a 1 in n factorial chance of getting an ordered deck. Well, think about a 52 card deck. 52 factorial is 1.24 times 10 to the 67th. So a 1 in 1.24 times 10 to the 67th chance is practically 0. The possibilities of getting an ordered deck statistically are very, very unlikely. Let's move from playing cards to chemical and physical systems. And when we do that, we're going to start to talk about the word entropy. Entropy is often described as randomness, but really a better way of saying it is entropy is a measure of the randomness of energy distribution. And what we've seen with the deck of cards is that having an ordered deck was very unlikely. Having any of the many possibilities, the 23 other possibilities of a disordered deck, is much more likely. So higher entropy, higher randomness of energy distribution is one of the driving forces behind spontaneity. Nature seems to prefer having the energy more randomly distributed. Here's another way of thinking about it. Imagine that you start out with a car. Here's our little green race car guy. And you have a full tank of gas in this car. And then you start to move. Well, one of the things that happens is as you're moving along, the radiator throws off a lot of heat. In fact, that's going to turn out to be most of the energy that you're going to burn as you're going down the road will be wasted as heat. And so that loss as heat distributes that energy more randomly than it was before. It used to be compacted in the tank, now it's distributed. Another thing that happens is friction of the air flying past the race car, and the friction of the air on the roads creates a little more heat, and that warms up the air, and it warms up the tires, and it warms up the road, and that all eventually ends up warming up the air and distributes that energy more randomly. If the lights are on, then light energy bounces off trees and roadway and bridges and things, and that all ends up as heat energy distributed through the air. If you sound the horn, those sound waves end up as heat in the air. And when you finally come to a stop, the friction of the brakes on the brake pads will distribute even more heat into the air. So by the time you finish this entire trip, all that gas, which was once concentrated in the tank, has now been distributed along the 500 miles or whatever of air that you've driven through during the course of that trip. That represents an increase in entropy. Instead of all being concentrated in one place, that energy is now all distributed randomly throughout the air along the roadway. The greater the entropy of a state, the greater is its statistical likelihood. It's much more likely, if you took a bunch of energy and just threw it into the universe, that it would be randomly distributed than it would be concentrated in, say, the gas tank of a car. And since these arrangements of more random distribution of energy are statistically more likely to occur, changes that result in energy being distributed more randomly tend to be spontaneous. In fact, there's a law. This isn't just sorta. This is always happens kind of a thing. The second law of thermodynamics, pretty famous law, says whenever a spontaneous event occurs in the universe, it is accompanied by an overall increase in entropy somewhere. So more random distributions of energy tend to be spontaneous. Entropy change, it turns out, is a measurable state function, so it doesn't depend on the pathway that you take from start to finish, like all state functions. It just depends on the starting and ending position. Now, if delta S is positive, in other words, there's an increase in entropy, an increase in randomness, this favors a spontaneous reaction. That doesn't mean that it has to be spontaneous, because we have that other factor, that energy change in the system that we have to consider. But increases in entropy are one of the factors that favor spontaneity. And conversely, if we see the system get more ordered, in other words, if entropy change is negative, then that will tend to be a non-spontaneous change. So how can we tell if we're going to have an entropy change that's positive or negative? Well, it's measurable, so we can look things up and do calculations. But there are some simpler things that we can do to make general predictions as well. One thing is volume. Volume changes affect entropy. Take a look at this picture here. On the left, we've got a container that's got a divider between two sides. On one side, all these particles exist, and on the other side, it's empty. If we remove the divider and then walk away for 500 years or something and come back, there are two possible ways that we could find these particles arranged. This possibility down here is where the particles are all randomly distributed throughout the container. So they've moved around doing their constant random motion like little particles do, and they're now evenly distributed. That's very likely. It is possible, because all their motion is constant and random, they could possibly randomly have all found themselves in the same side of the container that they were originally. That's possible, but it's not very likely. It's extremely unlikely, in fact. So the particles being distributed into a bigger space or a higher volume is more likely than them being distributed into a smaller space or a smaller volume. So an increase in volume results in a delta S that's positive. So delta S is negative when there's a decrease in volume. Delta S is positive when there's an increase in volume in a system. Temperature change affects entropy as well. Think about these two systems. This is a molecular dipole. On the left-hand side, it's at low temperature, and so the dipole-dipole interactions are keeping these things organized so that they're lined up in a pretty strict order here. So this would be like a solid, kind of. If you give them some more energy and allow them to start vibrating, this is still a solid, but it's at higher temperature. Now these particles aren't quite as ordered as they used to be. There's a little bit of more random distribution that you can see going on here. Some of the particles are still lined up straight, but many of the particles are starting to jiggle around. At higher temperature, we have higher entropy, higher randomness. So delta S would be positive for a change that would go from this state to this state. So increases in temperature result in increases in entropy. State changes affect entropy as well. If you think about particles that are in the three different states, in the solid state, they're all vibrating around fixed centers. So we have these like face-centered cubic and body-centered cubic arrangements. Those are particular places where the particles have to be. That's very ordered. In liquids, we don't see that anymore. The particles are still close together, so they're occupying a small volume, but they're randomly distributed. We don't see these particles arranged in any fixed locations. In a gas, not only are they not in fixed locations, but their volume is much higher as well. They take up way more space. So the particles are least randomly distributed with a solid, so that is the lowest entropy. And with a gas, it's the highest entropy because they are the most randomly distributed that the particles could possibly be. So what do we do if we don't have change in volume, change in number of moles of gas, for example, or change in temperature? Well, the third law of thermodynamics helps us with this. Third law of thermodynamics is really kind of a definition. It says at absolute zero, the entropy of a perfectly ordered crystalline substance is zero. So that means you have a solid, all the particles are exactly on spot where they're supposed to be in the lattice formation, and it has no entropy. There's no randomness at all. So that provides us with a sort of a reference point. And everything can be measured based on a perfectly crystalline substance at absolute zero. So the standard entropy, there's a little degree sign, it means standard conditions, and S is the abbreviation for entropy. The standard entropy is the value of entropy for a substance when it's at 298 kelvins and 1 atmosphere. and you can look that stuff up. So therefore, it's possible to find the entropy change for a chemical reaction at standard conditions. And you would do that sort of like we did with Hess's law. The entropy change at standard conditions for a reaction is going to be the standard entropy of the products minus the standard entropy of the reactants. Now, these are not entropies of formation. These are absolute entropies for a substance at that set of conditions. And so, as you're looking these up in the charts, like when you were doing Hess's law problems, if you had an element in a standard state like hydrogen or tin or something like that, you could ignore it because its enthalpy of formation would be 0. But its entropy, its standard entropy, will not be 0 for any substance. So you have to consider all of them.